as we know, yes, okay. So as we know, we have the various components that we recognize. There's a mass on this, the 0, 0 element. There's a momentum density, time components, and the spatial components are representing internal forces. So there's a lot of debate on this. There's been a lot of debate recently on what these internal forces might mean for the proton and for ordinary systems in general. And in the classical case, on the diagonal we have pressure, and then on the sides we have the shear stress. So the mechanical properties of the proton, are described by this energy momentum tensor. But how do we probe this? And this is, what I spend my day hour of my living thinking about. So the one thing here is that, the way to, this is the energy momentum tensor. So the one way to couple it is directly through the gravitational field coupling. And this is something that was thought about so long ago in this article that is actually very clearly written by Pagels in 1966. And now this is a graviton coupling to the electron here. And look at how this equation is stunning in the sense that, you have the Dirac spinors here and the three form factors, and this parametrization, the way if you look at it, resembles entirely the modern parametrization that I'm going to show in a minute of the energy momentum tensor. So now, of course, if you look at the coupling here, this is infinitesimally small, and it will never ever be measured for sure. It's a granted thing. And why did Pagels write it this way? Well, the reason why he wrote it that way is that he found it interesting because he found that this was a way to put mass in the theory, and this is something that is for us to think about in a way. So the electron mass entered through the vertex functions and not through the propagators, and so that was motivating his calculations, even if he knew that this could not be measured this way. So so fine. So then later on there were more publications. There's this one. There's again it's a nice paper in which these quantum corrections are calculated. This is just to see the difference in general relativity between different methods. But we want to there's another way to access it, and this way was found by Shandong Ji. In 1997, when he made this key observation. He made this key observation that revolutionized our way of looking at this side of hadronic physics. And so he showed that this is, you see the parametrization here, you see that it is very similar to the one that was originally found by Pagels. Plus, we know here that this is now the interacting field theory of quarks. And we also is going to be a Q and G term, which is not separately conserved. And so Shandong pointed out that these matrix elements, all forward. So when the final proton momentum is different from analyticity, are different from the initial proton momentum analyticity. And so these all forward matrix elements can be accessed actually in electron scattering, similarly to how we would do for the momentum somehow, if you think about it. And the class of experiments that he thought about is this deeply virtual Compton scattering experiment. And so this is, for instance, a sketch of electron proton going into E prime, P prime, gamma prime. And so this is the prototype of all experiments, similar experiments. This class of deeply virtual exclusive experiments. And we know that this is a process that is deep in the sense that it involves a large momentum transfer, and that is also involves a large invariant mass at the same time. Even if the proton comes out intact, the final state invariant mass is large, and so this means that this is not your this is not an elastic process. It is an elastic process. So it is very specific. A very specific feature of this process, makes it interesting. And so the key point here was to prove that factorization was working, and this was done in a series of papers right after the original paper of Chandon, there was a series of papers that addressed this issue, and we now know that it is working. So the key observation is that, we're going from GPDs that are the matrix elements for this process. If you calculate the local operators, so the GPD moments, we see that these moments are exactly the second Nelly moments are exactly the form factors that enter the energy momentum tensor. And this is a table where I summarize the situation. So these are the second moments. And this is what we get from the operator product expansion, and they're called A20 is lattice notation, A20 and B20, C20, and these coincide directly with the energy momentum form factors. And okay, so yes, and so this is the current physical interpretation that we have. That we can then see that the J is related to angular momentum, and we can. Because of this combination, we can work it out, and the same way that the T0I components are going to give us the form factor A, and the spatial components are going to give us the internal force. So this is what I wrote here: the shear. Similarly, you can write the pressure in a static approximation. So yes, and these quantities are calculable on the lattice. That was there's the LHPC calculation that's been there for a while, and then there are new ETMC calculations, and this is something that the lattice people are calculating. They're calculating recently again. So, and you see the A, B, and C form factors here. The A in blue, B in red, and the C is small in the evaluations for the U minus D and U plus D here. They're managing to do lattice evaluations. So cool calculation that came out recently, that one and Shannon. You can also calculate these form factors for the gluon sector, and this is for A and B. And here the lattice results are these blue points, and we reparameterize this in a paper of ours where we look at exactly the constraints on the gluon distribution. So this is very important to have these parts too, to be able to constrain the gluon GPD. And I didn't put the full reference, I should have. So yeah, so summary of all this. So this is an introductory part. So there's been recent surge in activities to understand the various components of the energy momentum tensor. And so in particular, mass from the energy density, transverse spin and pressure. And so, oopsie, sorry. The response will not be found. This is my take on this. Not be found by debating the fine details, but which is also important. Okay, that we have these exchanges, but in the end, we have to figure out the way to measure and to validate the various hypotheses that we're making. So going beyond the energy momentum tensor definition, so these are the questions that I think are relevant and that we're going to ask. So can we understand, based on physical models, the various physical components of angular momentum, mass, and internal forces and pressure? Can actual measurements in the lab shed light on the orbital and spin components for quark and gluons? And then for the mass sector, there are a set of new questions. And so one question that is urgent, I think, is can we distinguish the Higgs mass component, which comes in like, with the quark mass multiplied by the psi bar psi condensate from the dynamical mass. Can we distinguish this part, the Higgs mass, from the dynamical mass, the part that comes from the quark and gluon interactions, and how do we see this in experiment? And so, and here comes the role of the trace anomaly, because we know the perturbation QCD has an important role in this. And then again, what are the observables for pressure and the internal forces? So I will focus on, so the first step here is to go from orbital angular momentum in the longitudinal direction that I have the feeling that we now understand well even if we don't have, a whole set of measurements on, to the transverse case. And I'll also, try to show in the end a summary of what the observables should look like. So the first step, I think, in order to address all the other ones, is to look at how we can go from longitudinal to transverse space. What does this entail? So, so we'll focus on the quark sector. Of course, there is a lot of interest in the gluon sector, but we don't have results that are in the shape to be shown yet, aside from the parameterization of the GPD, which is interesting. So, so we'll focus on the quark sector, and so the method that I'm showing here is going to be an alternative method to separate out the orbital and spin components that connects directly to the kinematic dependence of the observables. So the X, C, and T, the observables that the GPDs depend on, and that can be measured or extracted from lab measurements. So yes, this is a general slide on Lycon variables. This is what this is important. This is what we're going to be referring to. So all that we can say, okay, for angular momentum, is based on this isomorphism between the Galilean symmetry group of non-relativistic quantum mechanics in 2 dimensions, and the subgroup of the Poincaré group that leaves this surface, which is transverse to P+, surface which is in green here, invariant. And so in other words, whatever goes on this surface can be treated with our non-relativistic intuition. And this is important. And so the here is something that I shouldn't be writing this way, and I should be correcting. The Lycon Z- variable is called the Joffre time. This is not the Z- variable. What is the Joffre time is what I wrote here in red. It's not the Z- variable along the whole axis. It's just the time, this time where the interaction, where the deep inelastic scattering interaction takes place. That is written in this red sector here. Okay, so but the point to make here is that we can write variables, momentum variables, and coordinate variables in both planes. But there is a subtlety here involved. There are really 2 distinct spaces, coordinate and momentum spaces together. So, there are 2 distinct spaces, and how do they look like? So, and why do we need them first? We need all this to define the Wigner distributions. So the Wigner distributions, again, I'm showing you the GPD diagram with all the momenta involved, and now I'm showing what is Lycon and what is transverse in some sense. And so you see that for a generic operator gamma, we can write it this way in between the 2 quark fields, and you see that the quark fields for a Wigner distribution can be so depend on Z- and ZT, and also and KT and K plus, which is XP plus, is conjugate to Z-, and this in red is the first set of variables. The other set of variables, momentum and coordinate variables, the other space, is the space in which delta T, this difference between the initial and final quark and proton momentum, and BT vary, where BT is the is just the conjugate to delta T, and this BT defines the position of the quarks inside the proton, while delta T is just the difference between the proton momenta, and this is what is conjugate to, and the other 2 conjugate variables are ZT, which is the distance that represents the distance between the place where the photon is absorbed and re-emitted, and the transverse momentum of the partons. So the transverse momentum is not conjugate to B, in other words. So there are two distinct spaces, and this is what we play with when we work with Wigner distributions. And Feng, who was here at least, is an expert on this because he wrote along with Belitsky and Chandon, I think the first paper, one of the first papers at least, on Wigner distributions in hadronic physics. So all of this is good. So the Wigner distribution is useful when we define it in terms of KT and B, because now we can define immediately a longitudinal angular momentum by taking the cross product in the transverse plane. So like B cross KT. And this is what we consider the orbital component of angular momentum. So can this be measured? So this is more of the above. The first step to do here is to identify this with this quantity here, which appears with this generic Wigner distribution, with these functions. Well, there is F14 and G11, and these functions are generalized transverse momentum distributions that have been parameterized in a complete parameterization given by Massner, Metz, and Schlegel, and I have a reference to their paper in the following slides. Should be here too. And so this is the first step. So here we can connect these Wigner distribution to GTMDs that are actually quantities that are close now to observables, because they're the quantities that we parameterize our correlation function. And so so the other way that the orbital angular momentum was known is through this sum rule that was written in a paper by Polyakov and collaborators, and in a non-interactive theory, and then by Hatta with a full treatment of the gauge lengths back in 2004 and then in 2012. And so they noticed that using the operator progress function essentially and calculating this moment of the GPD, the second moment, that there was this, that the twist 3 GPD object, this XG2, which is a twist 3 object, could be written as the difference between these two. And then if you identify this with J and you identify this H tilde, which is the axial vector GPD with the longitudinal spin, then obviously this twist 3 GPD has to represent orbital angular momentum. But the question is why, and what did this have to do with the F14 definition that I was given before in terms of our Wigner distributions? So there seems to be some kind of a disconnect. Well, so here on the left-hand side, I'm going to summarize what was done. So using the operator progress function plus the QCD equations of motion, one can show that the second Mellin moment of a twist 3 GPD, which is G2, can be decomposed into a twist 2 part that depends on the second moment of the twist 2 GPDs, H plus E. So I'm summarizing what's in the previous slide. And yes, and then this we can look at the role of this, especially interaction independent part that we'll study later on. So we know that the twist GPD comes in as a difference between the moments of H plus E and H tilde. And on our side, what we propose here is instead of using the OPE, so we derive the different terms using non-local matrix elements only. So we start from the unintegrated in X parts, and we what this approach affords us is that we can throw in there transverse angular momentum, the transverse momentum, the Parton's transverse momentum. So the transverse Parton momentum plays necessarily an important role because we're looking at the correlation functions. And also this method is very versatile. So we can change the operators very easily and very easily get, very easily. My students are going to slap me. So we can, in a physically straightforward way, find the relations. So so this is what an equations of motion relation looks like. So we take this operator, which has the I and plus gamma matrices in there, and apply the equations of motion. And so there's going to be another gamma matrix coming from the D slash, and then with the relationship between the three gamma matrices, we can elaborate this relation, and we come up with this. We break up the energy momentum tensor into all of these pieces. So there's going to be, in this case, because of the choice of operator, we get the axial vector pieces gamma I, gamma 5, and gamma plus gamma 5 of twist 2 and twist 3, and the vector pieces of twist 2 and twist 3, plus this term calligraphic M, which comes from the transverse gluons in the D slash. Okay, so then when we can take this for x equal to 0. These are for GPDs, so they depend on, so delta plus is related to the variable C and so on, but we can take the forward limit and directly here, and so you see that when you write down the various if you take the right helicity combinations here, so the lambda prime and lambda equal to plus plus minus minus minus, they give you a spin for the proton and the net spin. So you see that you get this GPD e to t tilde, where now we are sort of like abandoning the naming given by Polyakov, but we are adopting everything within the Meissner, Metz, and Schlegel scheme, because I think it makes sense to have this one, complete paper to refer to in order to avoid, confusion. So this e to t tilde, that will be related to G2 in what follows, and it's a function of x, and all of these are a function of x, and so you get H tilde, and then you get this F14 moment, where the F14 moment in the all forward case is defined in this complicated way for a generic function x. And the important thing is to see that this F14 moment in the forward limit for delta t equal to 0 reduces to a KT square moment. So this is your good old KT squared KT square moment, and then the QGQPs. Okay, so now we need the Lorentz invariance relations to this. So this is a relation. This is a relation that holds, and it's interesting in itself, if you wish. So now, but we have that F14 KT square. So we want to still make the connection with the Polyakov result, the Polyakov and Hatta result, and we still want to understand if there's something that brings us closer to measuring the orbital part than a GTMD. GTMD is good, but let's see if we can find more. So so Lorentz invariance relations. So the Lorentz invariance relations establish a connection between these KT square moments and the twist 3 GPDs. So why is this connection there? Well, it's going to be a little bit involved, but the connection is essentially a consequence of the fact that all the possible helicity amplitude combinations that I can form for all the, with all the GPDs outnumber the Lorentz structures. So when we write the covariant Lorentz structures, okay, there are less of them that are needed than the ones that form the various helicity structures. So there are just a mismatch in number. And so let me give you an example. And this is the example here. So for instance, at twist 2, this is what the correlation function looks like, the helicity structure. So we're going to have an integrated one. So these are the GTMDs. So there's going to be a delta lambda prime lambda, so a non-flipped part, which has these GPDs, GTMDs, F11 and F14 in the vector sector, and a flip one. And this involves these GTMDs. And so similarly, we can do the same exercise at twist 3, and there's going to be now 8 of them because of the various of the symmetries of where this the back component can be placed. So so we can do the same exercise. And so now you see that this term here is the covariant structure of the tensor before we integrated to get to the GTMDs. And so you see that you have the number of amplitudes is actually smaller, and so then the GTMDs. And so you see that these amplitudes are now numbered like A1, A2, A3. There's an A4 missing here, and so on and so forth. And you introduce this A17. There is not a sequential number. And the reason why there is not a sequential number is because we chose a parametrization that didn't have the gauge link in there. So this is the straight link. For this example, I'm giving you the straight link parametrization. And we named, so this parametrization was given for the general case in Meissner, Metz, and Schlegel. So there was the full, all of the amplitudes are there, A1, A2, A3, A4, all of them. But we gave, we kept the same notation, even if we have a smaller number, not to generate confusion. So this is why they're not sequential. So okay. So as a result, you see that this is how you write the GTMDs at twist 2 and twist 3 that I was showing you before. And you see that now, for instance, A2 appears here, but it also appears here. Let's take, I don't know, A5. There's A5 appears here and also appears here. So there is a similar, some of these covariant structures appear in both. And that is what generates the Lorentz invariance relations, connecting these functions. That's all. And this was found long ago in papers by Mulders, Bacchetta, Mulders, and Mulders et al. Mulders and Tangeman for the original von Zurablicek relations between G1 and G2. So okay, whoopsie. Sorry. So okay. So now all right. So from here, that's why we can write this Lorentz invariance relation. So F14, we can write it as a function of the GPD E2 T tilde plus H plus E. And so this is what allows us to identify angular momentum. So to make this connection between the twist 3 GPD and the twist 2 GTMD, and this is this E2 T tilde plus H plus E is the same as G2. Okay, and that's the paper with all the notation. So yes. So of course, this can be generalized to sorry, my phone's going off. This can be generalized to writing the Lorentz invariance relation for a staple link, and this is the Lorentz invariance relation violating term. So okay, so this was for longitudinal angular momentum. This is for longitudinal angular momentum, and the results are written in these papers, and so we have these relations at the X level that we can actually go out and measure and verify. And the interesting part, so this is for a straight link, this is for a staple link. And the interesting part is that when we integrate these relations, we obtain the orbital angular momentum summation. Okay. So now that we played this game here, oh yes. So one more question about the two different projections of genuine twist 3 terms. So we have the one that comes from M and the one that comes from A, which is the Lorentz invariance, the gauge link piece. So the one that comes from A comes directly from the the transverse gluon exchange in the D slash operator. Okay, and so in experiment, we cannot measure these two separately. They're always going to appear in the formula in the equations for the cross sections and asymmetries together, unless we do an experiment that is aimed at measuring GTMDs specifically. And so the staple link component can be, however, determined in lattice QCD, and that's what we are relying on. And this is a calculation of Michael Engelhardt, in which you see this is a slide from him. We started from G to Jaffe-Manohar quark orbital angular momentum, and you see the G term is for staple link, for straight link, so there's no, it's at 0. This is versus the length of the staple. And the Jaffe-Manohar is going to be on the sides, the minus infinity or plus infinity. And this is what the lattice calculation at infinity averages to. And so you see that this quantity can actually be determined on the lattice. So now transverse angular momentum sum rule. So we want to repeat this exercise for the transverse angular momentum sum rule, and we can indeed do it. And so so this is how the transverse angular momentum, so we're repeating the steps, but now we have to go so we have to form we have to take the helicity structure that is good for angular momentum. So this is going to be the plus plus minus 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 components in the transversity basis, so either X or Y, and this will correspond to the spin flip elements of the correlation functions. So there are some differences here, of course, and but we proceed through the steps in an analogous way. And there's also another difference that is interesting, and I don't remember if I have a slide on this or not, but let me just say this. There's another interesting difference with respect to the longitudinal case, and in the sense that here we have to have delta t and xi. We cannot take the xi limit, the xi that goes to 0 limit from the beginning, but we have to keep xi until the very end, and then eliminate it. In fact, you see that xi remains in here. This is a xi odd piece, and it remains in here, and this is because of the different, transformation properties that transverse angular momentum has with respect to longitudinal angular momentum for yes. So for boosts in the so how the transverse momentum varies when we boost the system from the rest frame to the infinite momentum frame, and this has been addressed in this paper by also addressed in this paper in a different way than us by Yushin Wu, Shandongji, and Kaya Shields, and as well as other papers, Ji and co-authors, and Feng is one of the authors again, a couple of years ago. So yes, here is how we construct this, and so you see that we keep the delta terms in there. And we form the plus minus component, the plus minus correlators that correspond to exactly a transverse spin, and we derive a similar relation to before, only that now instead of having H tilde that gives us the longitudinal spin, we have H2T prime, which we identify with transverse spin. And these terms will go away when xi is taken equal to 0. And then we have, okay, also this term is going to be subleading. And then we have, so with this combination of GTMDs, F141 as before, and F121, I should say also divided by xi, because also F121 is xi odd. So okay. And so it is exactly analogous to before. And so now this allows us to identify this piece in here with the transverse angular momentum. So it allows us to identify which GPDs, twist 3 GPDs, are going to give us the twist 3 piece. So yes, and that's what we have. So we have an analogous sum rule, and we're in the process of sending this out for publication. So this result is new. So again, so we are able to identify the twist 3 GPD that defines a transverse spin. How does this all get together? Let me put all the pieces here. This was supposed to be animated, but let me just show it in one slide. So one way to look at this that I think will be interesting from a phonological point of view is just to put all these variables together. Now we're looking at the longitudinal one, and we can do this for the transverse one, and then your variable of choice. So we're looking at the U minus D piece because it's the one that we know best. And so you see that there are the lattice GPD moments, and this is the lattice calculation of for F14. This point actually here shifted a little bit to the right. I have to update this graph, and then if this gets into a publication, this will be done. And then you see that in order to see if this relation is valid, if this sum rule is valid, all of these, so this delta sigma, so plotting J versus L will give you delta 1/2 delta sigma as the intercept at 0 here, you see. And so you get this line, this red line is going to define your delta sigma, and then you're going to have, okay, J is of course on the horizontal line, and L is on the vertical line, and you see that the 3 lines have to intersect if if our evaluations from whichever lattice or experiment get it are intersecting. And here I put there's much more to say here about what can be done and what under what circumstances these lines are intersecting, under what circumstances we can actually compare the lattice with experiment and so on and so forth. All right, so how do we measure all this? What time is it? 7 a.m. Yes, I showed just a few slides on this. You know that there's this Center for Nuclear Photography that we're working, we're really enthusiastic about here in Virginia. And so we are working on the formalism. We're working on several ways to measure this. This is my point of view, very personal point of view, and then we have papers on this published. So this is in the demystification of the Harmonix formalism, and I was hoping to see experimentalists here too, but I don't think there are in this crowd, because this is very important. So is it good? I'm asking the question: is it good to break down your cross section into various harmonics, or should we look at it from a different point of view? So for me, from years of experience in coincidence experiments and so on, this DDCS is a coincidence experiment in which you detect in coincidence a photon and a final photon, an electron and proton, and of course they're gonna end up in a plane that is not the same plane as the original electrons, so not the same plane as the scattering plane. And so there's a scattering plane and there's a hadron plane at an angle phi, and so your cross sections will depend on phi. But how do they depend on phi? That is a separate question. So in order to ask this question, we should. So I'm showing this humongous slide, and I apologize, but it's not, if you think about it, it's not that ugly and monstrous, in the sense that there's a twist 2 sector up here, the twist 3 sector up here, and here I'm showing the various GPDs that enter transverse orbital angular momentum, the longitudinal orbital angular momentum, the spin orbit terms, and where they appear in with respect to the beam and target helicity. And so you see that there are many So this is a little bit at the bottom of my demystification of the Harmonix formalism, in the sense that you see that these GPDs, because they enter at the amplitude level, they appear pretty much in each and every one of the observables. And so there is very little differentiating among the different observables. It's like, if you think about it, the form factors, the Dirac and Pauli form factors. So they appear in, the Pauli form factor, which is a spin flip part, doesn't comes in, in the polarized case, right? So it's not, it's a situation that is completely analogous. So so that's just to make this point, and apologies in this IU. And so the first thing that we can look at is what the Bethe-Euler process, which is the background to DBCS, in which the electron is emitted from the photon is emitted from the electron, either the initial or the final one. And so you see that in the Bethe-Euler process, you can write the cross section. We did this exercise and we wrote it, and this is published. You can write it as exactly as you would write the elastic cross section, with an essentially electromagnetic form factor squared part and the magnetic form factor squared part with coefficients. And now depend on all the kinematical variables, which, yes, they're more complicated than in elastic scattering, but you can write them in this simple form. This is exact. This is in the unpolarized case. U means a polarized beam, unpolarized target. You can write them exactly like this. So in terms of 4 vectors, and it's not it is not at the end of the calculation, you have a very simple result. And you can define here too a longitudinal to transverse polarization variable, and this is conducive to thinking about doing, for instance, so similar to what you would do for the elastic scattering. Okay, this is the elastic scattering cross section with your polarization variable, which is longitudinal to transverse polarization variable, which is here, which is of course different from our case, and defined without the kinematics. And so what is this good for? Well, this is good for the following thing. Come on. Suspense. Okay. Yes. Oh, well, first of all, this is a simplification over the Harmonix formalism. This is just one good reason to just think beyond the Harmonix formalism, and I'm just flashing it here. And then you can move to the DBCS Bethe-Euler interference term and write something very similar. So now you're going to have similar coefficients. Okay, the coefficients are going to be a bit more complicated because now you're having the 2 processes together. So this AUU and BUU and CUU, I didn't write the forms because they have more form factors, and they're like, instead of being 1 line, they're like 4 lines. So it's pointless for me to show you all those 4 vector products. However, trust me. So you have an electromagnetic, quote unquote, piece, which has a little bit of magnetic in there too. A magnetic piece, which is GM times, look at this, H plus E. H plus E is just the angular momentum part that we need. And then there is a part which will be parity violating in the Bethe-Euler case, or in the elastic case, because, but it's not parity violating here because the 2 photons are distinct. And so we can have a GM times an axial part. This will be the GMGA in the parity violating space. So this is another way of writing the cross section. And then we can have linear plots instead of chasing these harmonics. We can write linear plots, and this is how we can do a Rosenbluth separation of what would be otherwise this type of behavior of the data. And so from the Rosenbluth separation, you can understand, some features come out immediately. In particular, you can measure H plus E straight out of your unpolarized target data. Okay, so and that's the only hope, I think, that we have to go beyond, twist 2 to get your orbital angular momentum variable. which is with coefficients which are however very small, as we are showing here. This is the smallest of our, the CUU over BUU is the smallest of our coefficients for the twist 2 case, and the twist 3 case is comparable to that. So let me conclude because it's time. And so so we presented an avenue to identify observables that are sensitive to both longitudinal and transverse orbital angular momentum. And so Jefferson Lab at 12 Jeff and the EIC will make history as we uncover these mechanical properties of the proton. This is a unique chance that we have right there. And this is why the Center for Nuclear Photography exists. And so an outlook, well, there is so much to do. So there is so much to do that it's always hard to write an outlook. And so so we can extend this to start thinking about the mass composition. We can extend this to start thinking about the gluon sector, and that's a wide open field. Nuclei are almost also wide open. If you think about, I love the spin 0 one. I love helium-4 because of the perspective that you get on the EMC effect there. But you know, the deuteron just as well. And of course, to do this, it will be beneficial to introduce, you know, state-of-the-art, at least, you know, machine learning dedicated analysis for the extraction of these quantities from the data. And this is something that is also a fascinating field that I couldn't obviously touch upon. So thank you. So this is all.
Excellent. Simonetta, thank you very much for an excellent talk. We have time for questions, if anybody has questions. Simonetta, I would like to know, you said that you love helium-4, but I missed why. Something about the EMC effect. What did you say?
Yes, I love helium-4. Okay, in this set, so for several reasons. Well, first of all, helium-4 it's a great nucleus because it's a small nucleus that we still have a lot of understanding if you think about it in terms of you know, momentum distribution, spectral functions, and all that from the point of view of two-body systems. Okay, it is something that is attackable in calculations, and you can you know, really be quantitative about. And at the same time, it's a very compact system. Because all of a sudden your binding energy goes, you know, from 7 to 28, boom. And so that makes it a very compact system. And so it's very interesting to study because we expect the effects like the EMC effect to be, you know, bigger. So that's why it's interesting. And from the point of view of all of this spin physics and GPDs and so on, and twist 2 and twist 3 and you name it, helium-4, the cross section is simple, even with all the polarizations involved, because you have essentially one chiral even GPD at twist 2, one chiral odd GPD at twist 2 that you can, you know, look at in pi 0 electroproduction or other means, and only two twist 3 GPDs. So for the study of twist 3, and these twist 3 GPDs are very interesting because one is the unpolarized piece. So one is it's a round one, like H, like the twist 3, you know, component of H, it will be. And the other one is an LU kind of correlation. That means it's a longitudinally polarized quark inside an unpolarized proton nucleus system. And so this is very interesting because it still sheds light, even if it's an unpolarized system, it sheds light on the spin orbit pieces. And so yes, so this is why, you know, it's, yeah, I haven't you know, fully written this part, and this is something that is like I think fantastic to propose, you know, to work on. So I'm hyper enthusiastic about helium-4. I apologize.
Excellent. No, I love it too.
Helium-4. So, yeah. Yes.
I have another question, but I'm going to wait to see if anybody else has a question.
Sure.
that they want to ask. So Simonetta, I want to ask about this mass decomposition. Like, so you take the gluon, the quark effective mass in the proton 363 MeV about, and try to distinguish it from the few MeV quark mass. Is that the idea?
No, so in the quark mass decomposition, so there is a paper, an original paper again by Sheldon G, and then you know, more papers followed, and then especially recently there's been, you know, a lot of activity in this sector. And so in that original paper, he showed how in the quark sector you can so you can separate out the part that comes from the M of the quark. So the bare mass, if you think about it, and that comes in, of course, in your correlator multiplied by psi bar psi, which is again this identity, you know, twist 3 quantity. And so and so that's what I call the Higgs one, in the sense that it gives you that bare mass piece.
Yeah.
And then the other part comes in, is like it's in some sense like the energy. I mean, it's a mass slash energy, in the sense that it comes from the d slash of the operator, of the Dirac operator. So you have the ID slash minus m. So d slash is going to give you the energy mass in the sense of energy, so the dynamic piece, and the m is going to give you the Higgs part. Now, yes, so this can be identified. So that the d slash part you can identify with the average value of x, you know, of you know, like the momentum distribution, if you wish. And the M part, you can associate it to a twisted GPD. However, I think that there is okay, and then you go, and then there's the gluon part, which is you know, complicated to. Well, you can also see that as an x sub g, and the a lot of attention has been given recently to you know, the renormalization group, so the trace anomaly. So, but I think that so what I would like to see here in the future is a relation that by which we can write, say, maybe we could write, you know, like these two pieces that involve the quark with a Hamiltonian. And so have again a three ways sum rule. That's my, just to lay bare my
ideal.
I think, yes, the idea, yes.
But yes. Simonetta, do you mean that, like, in that d slash term, I never thought of it this way, but in the d slash term, do you also include like the gluon Bremsstrahlung off the quark?
And that's yes, and that's where the physics becomes interesting. Yes, because
but it's also in the d slash. It's not in like a gluon sector.
Right.
I mean,
right. No, there's yes. Yes. How do you separate the quarks and the gluons? For the mass part, it's currently you know, very debated. So it yes. So there is I can yeah, I didn't focus on this because this is something that I started looking at more recently. But so the idea here is like, similarly to how going to transverse angular momentum, we could find these relations, okay? And so it would be great to find something similar that represents mass. But again, you have to go to higher twists, just like we did for the transverse angular momentum. That is higher twist compared to the longitudinal. I mean, that at least has a big, I mean, the interest in physics is in its higher twist component. And so that's a little bit the idea. If we can attack this here and going to higher twist in this type of relations. And so yeah, so this is what it is. However, there is so there's a PRD, the more extensive paper by Chandongji that sets the ball rolling back then.
Mhm.
And then there are several recent papers that are very interesting to read and that attack this problem. And it's a highly debated question.
Very interesting. Thank you. Well, if there are no more questions, then I will thank Simonetta again from all of us and see everyone next week.